Spring break can be a hard period for people to get away from family and kids. I have a feeling we might have our audience for today, but as ever, we'll have these recorded. I know a number of people have already watched the last one. And for those of you that don't know, we've got most of our webinars recorded and on YouTube. And if you search Denver Data Drivers, you can find us there, and you can rewatch almost all of the previous talks that we've had. I guess we will get started. Today, I'm really excited for another talk from Jesse, who's going to be talking about what I think is a really cool use of technology. Very often we kind of get lost in thinking about ways to automate everything and forget about how our role as geologists and engineers is changing, where automation can become sort of our right-hand man supporting our interpretive work and our technical roles. Today, he's talking about how they've developed a top picking algorithm that helps support the experts that would normally be picking those tops. We've talked in the past, I think already we had a talk from Matt Bauer talking about dynamic time warping as a way of just trying to pick tops. And I know that Matthew Belabradich has done some work at Schlumberger trying to build some automation tools for top picking, and you run into lots of problems trying to think about how does the human work and how does the computer work and how to make them work well together. And so I think Jesse's work here really offers a new look at how a computer and a person can work together to make the work and the output better, and kind of establish a new process for how we should be picking tops. As ever, pay attention to the people up and down the participants list. There's some really great people. I kind of like to remind everyone that you guys are the group that's going to lead the industry in a new direction, taking technology and really using things to update workflows. So really awesome group. I'm always excited when I get to sit down and talk with individuals who are coming to these things, because y'all are doing some really amazing work and really thinking well about how to change the work of oil and gas. With that, Jesse, go for it. I'm excited to see what you got today.
All right. Thanks, Kurt. I'm going to go ahead and share my screen here. All right. And let me move the chat over to the side here so I can see. If you have any questions as we go, definitely, feel free to type in the chat. I'll try and answer them as we go through this. So as Kurt mentioned, today we're going to talk about everybody's favorite topic, picking of tops from well logs. So I want to start off and thank all of my students that worked on this last spring, Josh, Sonia, and Samira. They did a lot of the heavy lifting and kind of developed the proof of concept of, is this even a thing that we can do? So they put in a lot of the work, and then they pushed it 90% of the way, and then I just kind of picked it up and finished off the last little bit of it. And then also want to thank Michael Perch for, talking about this, discussing, is this a good idea? Does this work? Can we even do this? So it was definitely a team effort, kind of pushing forward on this whole project. And then also a special thanks to ConocoPhillips. They fund all of our student research, so we couldn't do it without them. And then also a huge thanks to the College of Natural Sciences here at UT Austin. All right, so just like last time when, gosh, that was a month ago, last month when I talked to you all, here's a brief outline for today. So I'll start off with a little bit of background. So what's the problem? Keep it fairly high level. And then we'll get into what is a recommender system. We'll talk about kind of the implementation or the theory behind it all, the math behind how it works. And then I've got a couple of notebooks. We'll run through a pure NumPy implementation, and then a PyTorch implementation, and kind of compare and contrast the results for a single test well. All right, so let's start off with a little bit of background information. All right, so what's the problem? Well, correlating formation tops is really, really time consuming. Typically it's the intern that gets the joy of sorting through a basin and picking tops, or re-picking tops. One thing that I always think of is how it's kind of circular. You start in one well and you're working across the basin, and even if it's a lithology top, by the time you get to the other side of the basin, maybe you've changed your criteria for how you're picking that top. Maybe it looks a little bit different maybe it looks a little bit different on the other side of the basin, and when you go back to where you started, it might be different. So you might update, and things tend to get a little bit circular. Next thing that's kind of an issue is everyone seems to be an expert. Everyone wants to pick a log slightly different. Some people will pick it at an inflection point, some people will pick it at a max, some people will pick it at a min. So everybody's kind of got their own personal preference for how they want to pick a top. And then the last thing is, are we talking lithologic tops, or are we talking sequence strat tops? It's a kind of a different ball game picking those. So this is kind of our underlying problem, is that it's time consuming, kind of circular. We got a lot of people that want to do it differently, and our tops can be different depending on how we want to pick them. So let's give this a shot. Really easy. We'll start on the left. So these are all gamma ray logs. The units are down at the bottom. And just for an example, let's pick this kind of break right here in this first log on the left. So if that's the top we're picking in the second well, where would you all probably pick that top? You stop me when I'm where you would put it.
The orange one, you passed it.
Like right in here?
Yes.
Yeah, so probably right in there. And then if we're going off kind of this similar pattern matching, and in our next well, maybe it's this thing here. And we can move, based on probably here, maybe. For this one.
Yes.
Yeah, so we can kind of pick our way across these things, even though these are just randomly chosen out of a field. But we've kind of got an idea, from experience of how we want to pick this top based on pattern matching is essentially what we're doing across here. So we're matching that pattern as we go from well to well to well. So it seems pretty straightforward, pretty easy for something like that. So we did some pattern matching. And kind of one of the key things we learned last month is that when we see things that are pattern matching, we should look at that as scientists and go, ooh, pattern matching. We can automate that probably. We can probably build some kind of machine learning. We can offload these kind of tedious, boring things. And then the last thing to kind of keep in mind is that human-in-the-loop systems with humans and machine learning tends to work fairly well. We can have a human pop in for maybe high-level stuff. Like we saw last month with aliasing well log mnemonics, having a human kind of saying, yeah, that's a good alias, or no, that's a terrible alias. That can work really well. So if we go forward with this, let's kind of think about, how can we deal with this problem? Well, there's been a couple of approaches so far. And just for an example of why it's nice to have this kind of stuff is, being able to replicate something like this based on a few well picks, these correlations, this level of correlation, this would be really tough if you're just jumping into a basin, or if you just got a bunch of new wells. If you're not a domain expert and have been working this certain area for several years, doing something like this can be a pain in the butt. It's going to take you a lot of time to kind of get up to speed with, what these log responses are looking like from up to down dip in a section. So ultimately, we want to build some kind of way to correlate these tops from log to log to log. So let's talk about the current solutions to the problem. So we've got dynamic time warping. This one's really popular right now. It works really well. I think it's really, really cool. I think it's a great solution to the problem. And I think kind of like last time, it seems like there's a tweet for everything. So here's some of what Zoltan here at UT has been working on with dynamic time warping. And it's cool. It works really, really well. You can see it's basically correlating log signatures from one well to the next. How does it work? It's more or less kind of stretching and squeezing the logs, pattern matching between wells. It seems, it seems easy enough. It does a pretty good job. Let's talk about kind of another approach to the problem. So we have dynamic time warping, where we're squeezing and stretching our logs, and pattern matching. Kind of the other way to approach this is from like a supervised learning paradigm. So in this paradigm, they're basically approached it as using a variety of different window sizes on the log, kind of sliding them up and down the log, and then pattern matching inside the different windows, looking for similar gamma ray responses or resistivity or whatever. So we've got kind of these two approaches. And our supervised learning, I say, again, it seems easy enough. It does pretty well. I think their error is, it's plus or minus about 6 meters. So it does a pretty good job predicting tops on their data set that they used. And also, PredictAdops is the coolest name you could ever come up with for a software. All right, so we've got these kind of two approaches to the problem. So let's talk about advantages. So time warping, dynamic time warping, you don't need a whole lot of human input, which that can be really handy. PredictAdops has really pretty decent accuracy. So for a sequence stratigraphic data set, 6 meters, plus or minus 6 meters, that's pretty good. Some of the shortfalls, the time warping, you've got to standardize your logs in every single well. You've got to make sure you've got logs for every single well. You've got to make sure that your logs cover, whatever zone of interest you're correlating. So you got to have some kind of standardized or normalized suite throughout whatever you want to correlate through. And then PredictAdops, pretty big training data set. I think it's like 300 megabytes, half a gig, something like that. So can be cumbersome to download, train, and kind of move forward with it. And you do have human input required. So you're correlating human picked tops throughout the data set. So that's kind of the trade-offs of these two. Everything, just like what I'm going to talk about today, has advantages, has shortfalls. The cool thing is kind of finding a balance between all of them. What works for some situations might not work for others, and vice versa. So we came to this problem and said, okay, how can we approach this problem a little bit differently? So the first thing that we thought of is, one day picking tops, I thought to myself, man, it'd be really nice if the software that I'm using to pick tops would just recommend hey, in this well over here, you pick the top of this formation at 5,000 feet. Maybe you should pick it in this range over here in this brand new well that you're looking at. So our thought was first, it'd be nice to have some kind of a recommended solution for this. So recommend the best tops based on either your picks or other interpreters. It seems like every piece of software now has this, we saw you like this, or we saw you bought this, or we saw you did this, you might like blah. Why don't we have this for picking tops? So our solution, we thought, it'd be cool to see if this even works. And then it'd be really useful for replicating picks from maybe people that retired, maybe that intern that you had for one summer that went elsewhere, maybe somebody that is on vacation, whatever. So it's a cool way to, maybe replicate picks from previous interpreters. Some of the advantages that our method has, we actually don't need well logs at all, which is kind of cool. So that means that if you have a well log that doesn't go to the zone you're interested in, you can still pick a top for it. It's a pretty lightweight model. All you need is a tops data set, so a CSV file with a well, a formation, and a depth. So that's all you need for it. It works with both lithology picks and sequence stratigraphic picks. However, we do have our disadvantages, just like everything I've talked about today. Some disadvantages: it requires human input, so you got to have a tops file to start with. And then it can be prone to interpreter bias. If somebody's picking it in a certain way consistently, and you mix in their picks with somebody else's, you're going to get probably some weird, interesting results back. So we definitely have advantages and kind of disadvantages of our recommender system. So next, let's talk about what is a recommender system, or a REXIS. And I was actually thinking about this today. Netflix it doesn't seem like Netflix really does this anymore, where they say, hey, we saw you watch all these movies about, X, here's more about topic X. Seems like Netflix now just says, here's what everybody else is watching. You should probably just watch what everybody else is watching. But like Spotify does it pretty well. Amazon does it pretty well, where when you use their product, you've had some kind of interaction with an item. Let's say I'm on Amazon and I'm like, hey, I need new brakes for my bike. And so I go to some page and I buy a pair of brakes for my bike. And then a couple days later, Amazon's like, hey, we noticed you bought that. Maybe you should think about buying brake levers, or maybe you should just buy a brand new bike. So they're more or less looking at how I interacted with some item and then making a prediction based on that. So in a very high level, that's what a recommender system does. It looks at some kind of interaction, either explicit or implicit. So explicit is me going on Netflix and saying, I like Braveheart so much, I'm going to give it 5 stars. So that's explicit feedback on some item. Amazon typically does implicit now. So, hey, we saw you were on a page for 45 minutes. That means you're either you're really contemplating this, or you got up and walked away from your computer. But it's some kind of way that they can measure how interested you might be in a product. And then Spotify does kind of a similar thing of you listen to, 45 hours of, I don't know, heavy metal. Here's some more heavy metal. And you can actually get kind of caught in these feedback loops of, hey, you just listened to the best of the 80s. Here's some more 80s music, even though that might have been a thing you were into for a day 2 months ago. So that's kind of the high level overview of what a recommender system is. So they're originally developed to recommend movies based on ratings, i.e. Netflix. The most simple case, and this is what I'm going to talk about today, all you need is a user, so me, an item, some heavy metal song, and some kind of explicit feedback. So in my case, I could say 5 stars, I really like that song, that's my explicit feedback. If you move up to more complex, you then bring in users, so me, items, my 80s hairband, some kind of implicit feedback. Well, I listened to it for 8 hours, 5 days a week. You might bring in where I listened to it and any other features that you can collect along the way. So that's kind of the simple versus the very complex. So you can get really wild things going on with the more complex version of it. In straight up math terms, what we're looking at is matrix factorization. So we're basically, we're just doing linear algebra, matrix multiplication And because it's machine learning, we're minimizing some loss function. So we're figuring out how to make the best predictions. So let's get a little bit more kind of nitty gritty on what is this thing. All right, so we have our prediction. This is our prediction right here. This should not scare anybody in any way, shape, or form. So our prediction is some latent vector matrix dotted with some other matrix. So we have our prediction, which will be in blue on this page. We have our latent vector or latent factors. And these are, we'll talk a little bit more about these on the next slide, but don't worry about them for now. They start off random and get better over time. So this is our item latent vector. And then we have our user latent vector. So these are just two initially random matrices of whatever shape and size we want. All right, so this is how we're making our prediction. So you can make a really easy, terrible prediction. You could just take a random matrix, dot it with another random matrix, and there's your prediction. And it's going to be terrible. So we got to train it. So to do that, we're using our loss function here. So we're just taking our actual, so our actual value of whatever we want to make a prediction about, and we're differencing that with our predicted and then squaring it. So this is our how close are we from reality measure, and then we tack on an L2 norm on the end over here, and this just helps us deal with overfitting, so that we're not fitting to random noise in our data set. So this is what it looks like kind of mathematically. We're just making some prediction with two random matrices, figuring out, yeah, that prediction was pretty terrible, and figuring out how should we update these matrices to make our predictions more reasonable. So in kind of a flowchart view, here's what it looks like. We start off, we've got some hyperparameters. So these hyperparameters, we've got lambda out here. So this is a user-defined parameter. You can do a grid search, you can do a random search, however you want to define your lambda. And that just helps with your overfitting. And then we have our random latent vectors. So these are however, how do I put this? They're whatever shape you so decide. So if you do a like 1 by n, that's typically what they use for a very, like an easy problem. A very complex problem, you'll do like a 7 by n size matrix. So the more complex you think the problem is, the more latent features you should have in these matrices.
Jesse, can you give an example of hyperparameters to help explain what you mean by that?
Yeah, so hyperparameters are things that we have to set before we start training. So they are things that the algorithm does not learn through training. So I could go through, well, so you pick like your dimension of your latent vectors, you pick whatever this coefficient out front. And these tend to be, you can either trial and error, or you can try a bunch of them and see what does the best. That's typically grid search, or you can just pick them at random and see what does best. And so these are things that we're not learning along the way. So that's kind of our two things that go into our recommender system. It sounds absurd as I'm saying it now, that we just pick this random matrix and just start dotting them and measuring how good or bad they are. But it works, and it's terrifying. So what we do is we basically feed in our hyperparameters. So we picked, maybe we have 2 latent vectors for each one of these matrices. And we've got some lambda value set here. And then what we do is we come in and we say, okay, let's hold our top latent vector. So we can say this one here, this yellow color one. So we'll hold this matrix constant, make a prediction. So we're calculating our prediction. And then we're going to calculate our loss. So how terrible is our prediction to begin with? And then we're going to update all of these values in this first, oh, sorry. Okay, so we're holding this first one constant. We calculate our loss. We come back and say, okay, how bad is it? And let's update these values in our second one that we're not holding constant. So update these values so that in a method that minimizes our loss function. So this is where we can get into, most people automatically think, oh, like gradient descent. Yes, very similar thing going on here. So in this case, we're going to alternate back and forth. So we're going to hold one of these constant, make a prediction, calculate our loss, update the other one, and then we're going to hold our first one constant, calculate our loss, update the second one, and we're going to alternate this, and this is called alternating least squares. And we're going to run this until we either hit a minima, so we're not getting any better, or we've reached some max number of iterations. So if I say you're only going to train for 300 steps, and it hits 300 steps and it's not in a minima, then it's going to say, okay, I've hit my 300 steps, and then it's going to return our final latent vectors and our predictions for it. So this is kind of the general workflow for a recommender system using alternating least squares. Start off with random, start dotting these things, measuring how close or how far we are, and then just updating iteratively until it gets either better or we run out of time. Any questions on this? Let's see. There is a question in the chat. Can you clarify if QI and PU are matrices or vectors? In the case they're matrices, the recommendation factor would be a matrix as well, correct? Okay, so these are going to be, so think of them as, part of me wants to say, consider them tensors. So they're going to be, they could either be a two, let's just say for sake, we have 7 things we want to predict. So we're going to have, we could have a 1 by 7, 2 by 7, 3 by 7, whatever dimension we want these to be. And they're going to return back a prediction for every pair of user item interactions. So it will return back a matrix when it's all said and done. And then we're just going to compare our actual, like our known values to our predicted values, but only where we have predictions, or sorry, only where we have known values. Does that answer your question? Excellent. All right, let's see, what's next? So this is kind of a more schematic view of what this looks like. So that previous slide was a lot of math. This is kind of what our tables look like. So we have some known values in here. These might be our depths, and we've got our formation tops and our wells. And so what we're saying is that we can fill in these missing values here by just multiplying our latent vectors for our formation tops and our wells. So that'll help us fill in these missing values in here. All right, let's talk about implementation. So we started off with this kind of interesting real world example in Wyoming that everybody knows and loves, the Teapot Dome data set. So we grabbed the data set, looked through it and said, okay, this looks interesting enough. Let's give this a shot. So it's Precambrian to Upper Cretaceous picks, and it's picked as kind of basically as a lithology data set. So here's kind of a type log for it, or like a merge type log, all the way from that's our Sussex top at the very tip top up here, all the way down to Precambrian down here at the very bottom. So this was kind of our first real world example that we were interested in. Can this even function? What does the data look like? Well, there's a whole bunch of weird picks in here. So we have formation tops. We have kind of down in the 10 sleep, we got a little bit of everything. I would, if I had to give an opinion, I would say that in this data set, from about the Jurassic up is the most robust portion of the data set, especially in the frontier. We've got a lot more picks through here, and then all the way up into kind of the Sussex. Once you get down into the Jurassic, the number of picks gets a little bit more disconcerting. And given that we have one Precambrian pick, you can't really measure how close or how far you are on anything that only has a single pick. Because you can make predictions in other wells, but you have no way to test it. So this is kind of an interesting data set. So our end goal for this data set is, we've got a variety of picks, and we wanted to make a pick in every single well that we have in the data set. And so here's kind of a quick and dirty what we documented in this data set is that, not surprisingly, as we add more and more data in, we get better and better results. So error decreases with training size. So the more data we feed it, the better it does. This data set, I don't know if I've got it in here. We ended up with anywhere from about 4 to 10 meters inaccuracy on our tops. So it kind of depends what you hold out and how you hold it out when you're picking these tops using a recommender system. But overall, it does pretty well. We use our mean absolute error and then a root mean squared error to kind of compare and contrast with predicta tops. So we can kind of get a feel for how does this method shake out next to predicta tops. Some other interesting things that we kind of document is that the variance in error. So this spread in our error actually decreases with picks per formation. So as each formation gets more and more, and as each well gets more and more picks, the variance kind of decreases. So we kind of settle in at this 10-ish meter range when we get up to our higher level picks here. One of the nice things that we saw is that our error is kind of, somewhat random. We do have some areas where we've got really low error kind of in the center here, and these wells just have a ton of picks compared to kind of what's around them there. So kind of interesting that we see this decrease in variance. So it's it's exactly what we would have expected, in that as we add more data in, we get better results. And then I think this is, so this is by the formation top. So each one of these is colored according to the different formations. So this is our Cretaceous chunk of wells here, and then our Jurassic is kind of through here, and then our Permian Carboniferous stuff is kind of over here. So we have a huge variance on it over here, but it kind of stabilizes out as we get more and more picks per top. Similar kind of situation for our root mean squared error here. All right, so that was, any questions on our lith pick methods? And I've got a whole notebook, and we'll actually kind of get into it of how this thing actually works. It's not all just show and tell. We're actually going to get to do some stuff. Yeah, so latent vectors, so they're kind of similar. Okay, so they seem really similar to neural networks, and that's exactly what your brain should be doing right now, is going, this sounds like neural networks. The only difference is we don't have any activation going on. So we're not really sending anything through an activation layer, but it's basically doing the similar architecture. You're just dotting, you're dotting two matrices and tacking on some kind of regularization onto the end with a bias. So it's very similar architecture. They behave in very similar fashion to neural networks as well. And you'll actually see in the PyTorch notebook, we'll go through it's really cool. We can just use neural network embeddings to build this thing out. All right, so I'll run through my last kind of real world example here. So this is the same data set that the gang over at Predictatops used. So this is the Manville group. This is a Cretaceous age sequence stratigraphic data set out of northeast British Columbia. And this one I would call a slightly more balanced data set. Everything's got, more than a couple hundred picks. So it's a little bit more robust. And we've got human pick transgressions and regressions all the way down to here. And then we just pick up kind of basically lith tops down here at the bottom. But everything up above that, these are all transgressive, regressive picks by people. And so for this data set, it's kind of interesting because we have such a kind of balanced data set as far as number of picks go. We don't really see any kind of change with our variance as we increase our number of picks per well. So it just kind of stays roughly flat. Our errors that we can measure kind of on a per well basis, we do see one area up here of a little bit higher and an area down here in the lower left where we do see a little bit higher error in these wells. But overall, we don't see any major trends. It's kind of independent of one another. So that's a pretty good sign that there's no underlying structure in this data that it's picking up on. And then this is kind of a similar plot. It's a lot less impressive, but this is just the number of picks for each sequence stratigraphic top pick. And so remember these kind of purpley colored ones, these are, this is like a lith top, and then these yellow ones are also like a lith top. So overall, I was hoping that we would see like, a big group of green transgressive ones and a group of orange regressive ones over here, but they're pretty interspersed. So we don't really see any meaningful relationship between error and the type of sequence stratigraphic top picked. So that kind of bodes well that it doesn't really care what they're picking. It's just more interested in where they're picking it. So the takeaway, kind of the big takeaway from the presentation part of this is from tops alone, our lith picks, our mean absolute error is about 4.5 meters. Our root mean squared error is about 8.5 meters. So not too bad. It's in the ballpark. Interesting things on the lith pick, I would have to say the biggest caveat with that is we assumed, here's our assumptions. We assumed all the wells are vertical. We didn't care about deviation. We just assumed they were all vertical for our purposes. So that might, if we actually calculated where these tops were relative to the surface, that might knock down our error a little bit. And then second, we don't know who picked these tops. It could have been one person, it could have been 10 people, whatever the inherent variance is in how they picked it. It's kind of a cheap cop out to say, wow, we don't know what the data looks like, but and there's a new data set out in the Netherlands that actually lays out who picked what tops. That could be a cool follow-up study to this, but 4.5 meters, I'm okay with that. Pretty decent. Our sequence strat picks, not so good. So our mean absolute error was 11.1. Our root mean squared error blew up. So 37.5 root mean squared error compared to predicted tops. They're at about 6 meters of error with root mean squared. So their method is significantly better than recommender system for that type of situation. Other things to take away, the more data you throw at it, the better it does. And then the more tops you pick and feed into it, the more your variance is going to decrease. And then the cool thing is that with this this variance, we can actually go through and calculate, okay, here's our error is plus or minus, 4 meters. We can actually say, give you error bounds on as you're picking tops and say, okay, here's where the recommender system thinks it is, plus or minus, some chunk of, some range to kind of get you in the ballpark. And you'll see a couple examples today in the Teapot Dome data set where you look at it and you go, this thing is terrible at this. And then you'll see other examples where it's within 2 feet and you're like, that's amazing. And then the last takeaway is, this can scale out to multiple interpreters. So you can scale this up to, everybody has their own recommender for how they want to pick tops. Everybody in the company's got their recommendations, and you can compare, contrast, you can pick new tops for people who are long gone from the company. So it's kind of cool that you can add in multiple interpreters with this method. All right, any questions before I move on to a couple of notebooks? While you're thinking about them, I'll pull this up. All right, so I've got 2 notebooks, and the first one is pretty much a recommender system from scratch. So this is using pure NumPy and producing recommendations. The big takeaway from these that I hope you really kind of ingrain is that probably 90% of the code in here is just organizing the data, just figuring out what we want to getting it into the right shape, and then actually training this thing is pretty straightforward. So we'll start off. We've got some kind of standard imports up here at the top. So we've got LASIO. That's just for 100% for Viz. So we can visualize this thing. Some data wrangling, visualizing, and then everything's going to be pretty much out of scikit-learn for our error metrics. And then this is for basically turning our matrix into a bunch of ones and zeros. And there's a question, were there certain lithologies or lith boundaries that were predicted particularly well or poorly? I'd say in the lith data set, the frontier actually has really good picks. And that's because we're looking at pretty consistent, I think there's like 200 or 300 picks per each one of those formations and up. So the frontier, we actually had really good coverage on there where the picks are like pretty believable. So areas where people have spent more time thinking about stuff and have kind of converged on a similar pick or have picked a lot, or things that are really easy to pick usually do pretty well. Things that don't have as many picks tend to kind of get into wondering what this thing is doing. And that's just based on it doesn't have enough examples to learn from. All right. So let's go forth in our recommender system from scratch. All right, so we've imported several packages, most for Viz, and then these next couple of lines. So I'm just, setting a path. Where is my well log that I want to visualize, and then I've got some color codes. And then I want to read in so that things match up as I pick tops. And then I'm going to set the API for the well that I'm interested in. This will just help me grab it out of data frames a little bit easier. And then this is this next cell here. So cell 3, I'm literally just reading in a cleaned up data set. So went through and verified that, elevations are realistic. They're not an order of magnitude off. That we're measuring from ground, or are we measuring from the Kelly bushing, and just standardizing our tops data set. This is actually generated automatically by a different notebook that can clean everything up pretty well. And then just kind of renaming some tops, or renaming some columns. And then we're just standardizing our subc values. So we're basically just scaling everything down on our data set here. And then we're going to drop out things that are missing because we're not really interested in them. And then we'll just print it out here. So here's what our data set looks like to begin with. We've got our API, we've got our formation code, measured depth, ground level. I think this is our datum elevation, datum type, and then our subc value here. Oh, our standardized subc value. So it's corrected from, we're basically subtracting our minimum subc value off the end of all our values here. Okay, so now let's pick our example well that I've chosen and just grab the tops and see what tops exist for it. So this is our example well. And so I'm saying, okay, let's just grab it. Let's query our data set and sort by measured depth. And so we can see we've got top of Niobrara, Carlisle, and a bunch of frontiers, a Maori, Muddy, a Thermopolis, and a Dakota pick. So that's all the picks that we have for the well that we're interested in for today. So now let's just kind of visualize this. I'm a very visual learner, so I like to plot these things up and see what they look like, plot the tops on there and just see what they're actually picking. So that's what we're doing here. We're reading in our well file from our LAS file, and then we're just going to plot it up with the tops. And so you can see we're starting out, there's not a lot going on at 0 feet, and then going down, there's tops in here, just nobody's picked them. So we go down and we've got our first top of the Niobrara here at, I think that's 2017. Keep going down, we've got our Carlisle top, and then we get in our frontier tops. So these are all of our frontier tops all the way down through here. And a Muddy top, Maori, Thermopolis, and Dakota, and that's it. So that's what they've picked in this well. So what we want to see, the end of this is tops, if there's a Shannon and Sussex in here, picked wherever it would recommend to pick them in this kind of upper section. And then, down here at the bottom, we'd want to see if there's anything in between here that it could recommend to us. All right, so that's just kind of a data viz portion. Now comes the data wrangling portion. This is the largest pain, is getting everything kind of into the correct shape to run through our recommender system. And so what we're doing is we're reading in our tops file and we're turning it into a sparse matrix. So we want it in the shape that you see down here where we have our API numbers. So each one of these columns is a well, and each one of these rows is our formation top. So remember back from the presentation, we have a user and an item. In this case, we've got a well and a formation top. And then everywhere you see a 0, nobody picked a top there. So you can see in this well, we have all these different tops picked, but we're missing this one. So this is the shape that we want our data set in, basically, to feed it in. And then kind of the key thing is that 88.8% of the tops were never picked. So they never picked 88% of this matrix. So this is kind of where we want to be. This is a good place to be. And then we're just going to turn it into a NumPy array. This is basically our NumPy version of our pandas data frame above. And then we have that scikit-learn binarized. This is a Boolean matrix here that says, okay, give me a 1 if there's a value there, give me a 0 if there's not a value there. And this is just so that it knows what was human picked. So it knows what is kind of the ground truth to be measuring off of. So these two will feed into our alternating least squares algorithm. So this is what does all our heavy lifting. This is all of our alternating least squares right here is this function. So what it wants our user item matrix with our ratings or our depth in our case. And then our Boolean matrix, so our 1 or 0. And then our number of factors. So this is our latent vectors. So this is a hyperparameter. Do we choose 1? Do we choose 10? Who knows? It wants our number of iterations, how many steps to run this thing for, and then whatever our regularization parameter is. So these last 3 items, these are our hyperparameters. And in here, basically what it's doing is it's going through, and with NumPy, it's basically going through and taking the dot product of our latent vectors, making our predictions, comparing them to our ground truth, and then updating whichever latent vector it's not holding constant, and then swapping. And that's 1 iteration. And so it runs through this whole thing and prints out, how things are going. And then at the end of the day, it returns back our users, items, and a list of our mean squared error, just so we can see how things progressed as we trained. And there's a question in the chat. Top's not picked. If you have eroded sections, would it force a non-existing top to be picked in all instances, or can you predict absence? So this is where it gets pretty interesting. So it doesn't. So if you have an eroded top, it'll pick it regardless. So if it's 100 feet up in the air is where the original top was, and it's been eroded that much, it will pick it 100 feet in the air. So it can actually, pick things that are no longer there, which is kind of cool. I do have to say, here's a caveat. We've not tested this in severely faulted or folded terrains with repeat tops. That is a whole different bag of worms. So in really folded sections, all bets are off. This is a pretty nice, broad, the teapot dome anticline is really nice, friendly play place for data scientists. Any other questions? All right, we'll move forward. Okay, so this is our function that pretty much does all our heavy lifting for us. So let's scroll down here. All right, so this next cell, I went through and we ran a brute force search. We just did a grid search of all of our hyperparameters that we thought could possibly be useful. And this is what we came up with. So we had basically two latent factors. So our latent item matrices are 2 by n. And our latent user items are 2 by m. Typically, as I mentioned earlier, the harder your problem, the higher this number is going to be. A factor of 2 or a value of 2 means that this problem isn't super challenging, which is cool. We're running for 290 iterations and then a regularization of 0.1. That helps us deal with overfitting. Once we've set our hyperparameters, all we have to do is call our run ALS. We throw our matrices in there, throw in our hyperparameters, and it runs through, and then we can just plot up our error function. And at the bottom here, we can see that our error got significantly better over the span of our 290 iterations. And you can see that it starts off super high and then decreases fairly slowly, and down towards the end here gets significantly better. Let's see, what else? Okay. So once we've run our training in our run ALS, we've done our alternating least squares. We now have optimized vectors. So up here, we have our users, we have our items, or we've got our wells, we've got our formation tops. All we need to do to get recommendations is just dot them together. So these are our latent vectors. We're just dotting them together, and boom, we have our recommendations here. So these are our recommendations in kind of NumPy form. So every single one of these corresponds to some depth to one of our formations. So we can look at it in a little bit easier to digest form if we move it back into a pandas data frame. So here we have all of our different formation tops for every single formation for every single well. So this is our data set currently. And remember, compare that with this one where it's mostly zeros. You know, we're missing most of it is gone there. And down here, our goal of having every single one filled in, we've got every single one filled in now, except for our Precambrian, but that only has one pick, so all bets are off on that. So that's pretty much what it looks like after it's run through and made its predictions. This next cell, we're basically denormalizing things. Remember, we standardized by our minimum subc value, so we're just denormalizing everything back to kind of like real world measurements. So we can actually kind of move back into real subc values. And that's what this chunk of code's doing. Let's see, what else? All right, so we have our predictions. We've got this well that we looked at earlier on. So now we can actually plot up our predictions on that well, see where it did okay, where it did terrible, hem and haw and have some fun. So we've got our predictions, so we can grab the well that we're interested in and plot them up. And so down here, we've got that exact same well log from earlier on. And then anytime you see a dashed line in here, this is going to be a recommended top. Anywhere you see a solid line, that'll be an actual human place top. So up here, if you remember, there was nothing up here. So it's placing the top of our Sussex here, base of our Sussex here. I have no idea how good or bad those are. We can scroll down and do the same thing with the Shannon. It's picking the top of the upper Shannon, top of the lower Shannon, base of the Shannon. That should maybe be down here. These ones are, I don't know what these log curves are supposed to look like off the top of my head. But you can see that it's making recommendations for where to place these things that nobody picked. So it's just recommending them to us. So now we're getting down here, and we've actually got something. We've got our top of the Niobrara that we can actually say, okay, how terrible or how bad did this thing do? 25, 30 feet off from the actual human picked example here. So in this case, not super impressive that it's picking it down here, but it's getting you kind of within the ballpark. As we move down, kind of a similar situation with the Carlisle down here. Pretty far, it's really underselling the pick. Same with the top of the Frontier Wall Creek. But as we look through the middle of our Frontier Wall Creek, these are all within, 10, 15 feet of the actual human picks in here. and whichever ones these are super, 5 feet or less. So they're getting you kind of within the ballpark here. And we can kind of see that all the way down through the rest of the Cretaceous, that this thing's kind of, it's definitely underselling, choosing to pick lower on average than the human human generated picks. And then you can see we don't even need a log. It'll just continue picking, and I'm all the way down to the bottom here. We've got recommendations here, and based on these other ones, you can say, yeah, they're probably underselling the predictions or the actual what a human would pick. So it's getting us in the ballpark. This method, this one with NumPy, does okay. The PyTorch one is a little bit more interesting. So let's move on over to PyTorch. And it's like, get this pulled up. Anybody got questions on kind of the NumPy version of it? I'll continue forward then in PyTorch. So right off the bat with our with PyTorch, you can see a lot of this code is, it's the same. We're just doing data wrangling. So this whole upper section is line for line the same. We're just wrangling our data, pulling it in, plotting it up. Exact same plot as we saw before. These are our human picks. And then some more data wrangling. Coming back, pretty much getting it into the exact same shape. And now here's where things diverge. So this is a really cool way to use PyTorch. I'm going to call him the grandmaster of recommender systems. Ethan Rosenthal has this great tutorial on his blog on how to do matrix factorization in PyTorch. And it's really, really cool. It's really clever. So what we're doing here is we're basically creating a recommender system class based on the PyTorch neural networks module. And so we're basically just going to inherit everything out of our neural network module. And what we're going to use is our neural network embeddings out of PyTorch. So that's how we're going to run our matrix multiplication, is with these neural network embeddings. And so all this class needs is the wells, or the number of wells, number of tops, and the number of factors. So how many factors we're interested in. In our case with NumPy, we had just our 2 factors for our latent vectors. And so what we're doing is we're basically saying, okay, let's just create an embedding. So we've got our first matrix, so our well factors. That's going to be the size of number of wells by the number of factors. So we're just creating a matrix the exact same size as our data set. And then we have our top factors, and this is going to be our number of tops by our number of factors. So this is creating our matrix. And I'm going to pull this back up really quick. So we are making these 2 latent vectors down here at the bottom with our neural network embeddings. This is what we're doing. We're creating these 2 things. So that's what these first couple of lines do. These next 2 lines, this is that regularization term that we had in there. So this is our bias that we're adding on. And it's just going to be number of wells. So this is our well bias. And then our number of tops for our top bias. So this is that regularization term on the end. Let's see, these next 2, this is initializing our matrices. I think this one, I think it's an identity matrix. I remember correctly. So this is just how we're going to start off and fill these things in with to begin with. And then we'll start off with our bias matrices as just zeros to begin with, and they can update over time. So this is all just to create those two matrices that we're going to dot together repeatedly and measure how terrible their predictions are. And then this forward method out of this class here. So this is where we're actually doing the dotting in here. So we've got our biases. We're just going to add those into our prediction, or I'm sorry, assign those into our prediction. This is going to be a, this will be a matrix. Matrix? Yeah, for each well and for each top, we're doing this. And then we're going to make a prediction. And here we're just saying, okay, let's dot our well factors and our top factors and just dot them together. And then at the end of the day, we're going to sum them, see how close or far we are. So that's our forward pass through. You might be wondering what happened to our alternating least squares. Well, we threw that out the window. We're going to do gradient descent in this case. So it's a little bit easier to use with PyTorch, and they've got like 20 different optimizers that you can use. So this is our class. So this is our recommender system class here. So if we scroll down, we're just going to grab slightly different hyperparameters. So we've got two latent factors. We'll just run it for 20 iterations and same regularization term. And then this next cell, pretty much all we're doing in here is we're just kind of reshaping our data, creating an instance of our model. Let's see, assigning or creating an instance of our loss function. Here we're going to use our mean squared error loss, just like we did in our NumPy Rexus. And then we're going to create an instance of our optimizer. And this one, you can go wild. There's all kinds of different stuff that you can use in here for optimizers, which is kind of cool. You get pretty different results for each one. Okay, so this last cell is the training pass. So you're basically just running through everything, making predictions, comparing your predictions to actual ground truth values, updating, propagating everything back through. Well, sorry. You're making predictions, calculating your loss, and then updating both latent vectors at the same time via gradient descent. So you're taking a step in the direction of more optimal every single time. And then we're printing out how close or how far we are. So this is our training pass as we run through every single row and every single column in our data set. So we can run through that and it'll print out. You can see our total mean squared error starts out in the billions of feet. And then by the end, we're down to 12 feet of mean squared error out of this method. So pretty decent improvement. Kind of a similar plot. We see, you know, increase from terrible down to somewhere near 0, 12-ish. And let me check the time. All right, I'm going to wrap this up. So then we run through the cool thing is we've now got a model that all we need to do to make a prediction is get the column number and the row number that we want to make a prediction on and cast those into tensors here and run them through our model, and it's going to spit out some number, and that's its prediction. So in this case, this is the A sand for the well we're interested in. It's saying the A sand's at 1,300 feet depth. So this is how we get predictions in this method. So we need to loop through every single column, every single row, run through, make our predictions. And after we do that, here's what our kind of end results look like. Remember, our dashed lines are model predictions and solid lines are human picked. So you can see here, our Sussex is a little bit more believable prediction. I think the original one has it somewhere super, super high. The Shannon prediction seems a little bit more in line with what I would consider more realistic. As we get down further, steel brakes. I think that's steel. You can see we're still seeing the same issue with this Niobrara. I don't know what is up with this Niobrara, but it does this for both methods. It kind of undersells it here. And then as we get further down, kind of a similar thing for our remaining tops. It's, you know, what is that? About 25 to 50 feet difference between them. But when you get in these areas where you have a lot more picks, you know, you're within 10, 15 feet of it here. So that one's actually pretty good there. So kind of a similar situation. It's underselling it in some places. I think this one does slightly better for some tops, slightly worse for others. So this is kind of two ways to come at the problem, two different methods, NumPy, PyTorch. Things that I think would be cool in the future is, you know, have this implemented for individual picks so you can, you know, kind of nail down is the differences that we're seeing in like this Maori pick. Is this an issue because somebody's picking it slightly different, or is this an issue because we assumed that all the wells were vertical? So kind of fine tuning it, I think, would be a really interesting step. As I mentioned at the beginning, this was really just a like, can we even do this? Is this even a realistic thing to have somewhere in the future? You're just sitting there picking tops and it's recommending where to maybe put them. So it'd be really cool to see somebody pick this up and kind of run forward with this top picking recommender system going forward. I tried selling this to a group of students this spring, and they started looking into that, and then they got sidetracked and decided to build a recommender system to recommend which wells a company should buy during an acquisition. That was what they were more interested in. So if anybody wants to pick this up and continue working on it, definitely get in touch, send me an email, find me on Twitter, find me on GitHub, and we can chat about it. With that, I'll go ahead and open up for questions, comments, thoughts.
I'll throw one out. You mentioned that using different optimizers yielded different results, sometimes better, sometimes less good. I'm always interested in the concept that the average of the models often outperforms any individual model. So when you say that you've got different optimizers getting different results, is that something that you see as a place for improvement where you could use more optimizers or use them in aggregation to figure out what's the right way to go? Or is it something that's more of quirks of specific optimization tools?
Yeah, that's a good question. I think throwing everything at it and seeing which one might perform the best. I think that'd be a great way to go. I'm a huge fan of brute force grid searches on things. So trying every single option, I think would be really interesting to, you know, and then dial down into it and say, you know, is there something inherent in this optimizer that makes it perform better at this task or not? Could be really interesting. Let's see, there's a question. Have you compared this accuracy to generating structural grids with a certain amount of withheld tops and then sampling grids to those well boards to protect your tops? I have not. And I've thought about this, you know, it's really easy to just make a isopack map or a structure map and say, why don't we just grab that top from there? Haven't done that, but one of the things I've thought about is that I kind of like about this method is that if you've got small faults, like offsetting things, it's really interested in the distances between the other formation tops. So it can actually pick up, like, you know, offsets on smaller flaw, like if you've got little blocks between things. So it'd be interesting to compare to like just a straight up structure map and see how it stacks up against that method. other questions? Yeah, and you know, one of the cool things is like coming into this whole project is like we've got a lot of options out there, and I think some kind of way of, you know, you might look at one set of like some problem in some field and say, hey, dynamic time warping is awesome for this. You know, this is just adding another like tool set to maybe consider for different situations. So it'd be really interesting to see kind of, I don't know, if somebody wants to come up with a way to integrate all of these, that would be really cool.
Can you talk a little bit about how you see or how you've used this or how you see students or teams using this? Because plus or minus 10, 15 feet is sometimes not so functional and other times can be huge for anchoring. So I don't know how you thought, or maybe it's something that you think more about a next steps for how to improve things.
Yeah. Yeah, so I think my first thought is like, you know, it can get you in the ballpark. Like that was kind of the original thought of this is, you know, correlating stuff around the Powder River Basin and thinking, you know, there's certain things you can pick really easy, and then there's other things that it's like, if I could just get in the freaking ballpark, you know, if I'm within 100 feet, that would help a lot. And I think pairing it up with something like Predictitops, where it's like if it can get you within 100 feet of it or 50 feet, and then you can run a supervised learning algorithm on 100 feet of your log rather than 10,000 feet of your log, that's you know, that's a tenfold decrease.
That makes a lot of sense.
Yeah. Let's see, there's a question. Are there geological reasons this would break down? For example, tops on either side of a growth fault or presence of unconformities. Can you tweak the recommender system so it would only use wells in a certain radius of the well to be predicted? Is it quick enough to do that? So it'd be really interesting to see in a situation where you've got like, you know, super thin or missing strata on one side of a fault and then a super thick chunk of on the other side of a fault. It'd be really interesting to see if it could learn that in certain regions, you know, it's going to be thinner versus thicker. And this is moving into kind of those complex recommender systems. So the simple version that we're using is just user and items and a depth. The more complex with factorization machines, then you can start throwing in things like locations and other kind of auxiliary information. I think locations would be really cool to have into this, and you know, it could learn wells in a certain region. You know, if you're on top of the fault, it's going to be thin. If you're, you know, like west of the fault, it's going to be thick. Or, you know, it'd be interesting to see how you could encode certain information like that into it.
Pelton Sylvester's done a lot of work, and they have sort of a different approach for how they are tackling some automated top picking or correlations, I guess maybe is more what they're focused on. But can you talk a little bit about how the differences between an algorithm like this and something more akin to what they're doing?
Yeah, so I think with this one, I look at it as, you know, this is a lightweight version. So they're correlating in their data sets. Well, their correlations for their data sets. One, their data sets have to be big. You know, you've got to have a matching well or a matching log for every single well. They have to be scaled roughly similarly. So you've got to spend a fair amount of time just kind of getting the data set in shape. Then it's going to be a fairly large data set versus ours is just a straight up, okay, here's our human information. Let's feed it in. I think the whole thing packaged, not including code, is like 2 or 3 megabytes, maybe. Definitely less than 10. So it's a lot lighter weight, but it does take that human aspect of it. You know, it takes the human component of people going through, picking different logs. So it is more of a human in the loop type correlation thing.
Gotcha. Does anybody else have something they want to ask? Well, Jesse, thank you so much. These are, oh, wait, there's one. Paul asked, as you train, as you're training towards a minimum error, is there a possibility that the system is fitting to a local rather than a global minimum? If so, is there a way to get out of local minima toward better solutions?
Yeah, so with the PyTorch implementation, you can actually set like a set momentum in there, so that if you're coming into some kind of a local minimum with a set amount of momentum, if it's just a local minima, it could potentially, think of it rolling out the other side, looking for other solutions. One of the things I noticed with the PyTorch optimizers is that without a learning rate decay, these things, they get towards a minimum and then they just start walking their way back out and getting worse and worse and worse over time. So definitely having some kind of momentum-based optimizer makes a huge difference, and then some kind of a learning rate decay where you're taking smaller steps as it's getting closer and closer to some kind of a minima really makes a difference for it.
Well, Jesse, this is a great talk. I think it's really cool work and really sparks some interest in ways we can do top selection and correlations, and thinking about the logic of some of the what seems pretty complicated as far as like correlating and picking a top, but can actually find ways to get an algorithm to support us and think about it better, as in what are we trying to do? What really is the work? What are we really paying attention to? And I always love it when a naive model can behave as well as some expert. You suddenly realize, well, maybe I'm not quite as smart as I thought. This is really, really good stuff. I really appreciate you taking the time to put this together for us and to walk us through both this talk and the one last month. As Jesse's doing some really cool work, there's some cool stuff happening at Texas. I think Michael Perch even has a sort of data science for geology or subsurface training through SCA, and then one on his own coming up. And so that's something worth checking out, people. Yeah, so thank you so much for giving the talk. We'll work on, I'm not sure what we have coming up next, but I know we've got more talks we're trying to line up for the year. If there's things you'd like to see, things you'd like to present, people you'd like us to invite, get in touch. If you're not on the email list and would like to be, as ever, always contact Mindy or I, and we'll get you on it. And we'll talk to you next time, and look forward to seeing you guys around town and wherever we come across each other. Thanks, Jesse. This is great.
Thanks for having me. I appreciate it. It's great to talk to you all today.
Yeah, I'll have to reach out next time I can find a way to get down to Austin and get in touch with some of the people in the program. There's some cool stuff happening over there.
Yeah, there's a lot of cool stuff. It's wild, talking to my freshmen, and they're like, I throw an idea at them, and they're like, yeah, and then they just run with it. It's pretty cool.
That's great. Yeah, I think it's been a long-standing problem that geologists tended not to be the coding group, and it seems like that's sort of changing in some weird ways. At least there's a subset that are, and it's yeah, I really like seeing what people are doing.
Definitely. Right on. Well, thanks for having me, Kurt. I appreciate it, and definitely
absolutely
be in touch.
We'll get a drink together next time I can make it down to Austin, or if you're ever up in Denver, we'll cover you for something. But I really appreciate you putting the time in to do all this. Thanks.
Definitely appreciate it, guys. Thanks.
And George, thanks for managing today.
Oh, of course. This is absolutely expanding my brain beyond, I need to decompress a little after your talks, Jesse, last month and this month. Really, really enriching and exposing me to quite a bit. So appreciate it.
Excellent. All right, take it easy.
See y'all. Bye.
See you. Bye.